started. Going to go over the exam 4 for today, and just let me also give you a little preview of the final in case you're starting to study for that. You know, as soon as exam 4 is, or maybe even now, start studying for the final. It will be cumulative. I'll take it from our 4 exams. I'll have your 4th exam available to you soon after you take it. Not on the same day, but hopefully soon thereafter. You can either come pick it up or you can get it online. And I can also send you your answers. If you can't come see me, just email me and I'll send you all the answers that you have. So just look at our 4 exams. We'll have a study session. See our exam. We'll have a study session. I'll send an email out, but we'll have a study session. I mean, it's 9th of December. That's a Friday at 3 p.m. That's after all the exams are done, so everybody should be able to make that. At 3 p.m., it's going to be in Beauregard 210. But I'll send you an email about that. December 9th, that's a Friday at 3 p.m. in Beauregard 210. That's one of these rooms up here. I'm not sure which one. December 9th at 3 p.m. Okay, but also I'll be around that week, so if you need help during that week, then please come see me. I'll be in my office. I don't really have office hours, but all my hours are office hours, and I'll be around largely from 7 to 3. If you want to make a special time, by all means, please do so. Just shoot me an email. Okie dokie? All right, so I also wanted to tell you about a special event that we're having on Monday. You might have seen this advertised. I think it was in the Nicholsworth. If you celebrate Christmas, as many of you do, we're having a special talk about the Star of Bethlehem, different theories about what people think the Star of Bethlehem was. Was it a comet? Was it a supernova? Was it a conjunction of planets? And so my wife and I are going to be talking about that on Monday night at 6 p.m. That's in the Plantation Suite of the ballroom of the Student Union. So if you like to come, that's fine. If not, that's okay too. But it should be kind of a fun talk. Now, let's think about our exam. We're looking at chapters 8 through 10. Remember, chapter 8 is probably the hardest chapter on this exam. It's the one with torques. We got a little bit into chapter 8 on the previous exam. We're going to see some of that similar material in chapter 8. That's dealing with torques, Newton's second law, angular momentum, energy, rotational energy, kinetic energy, work in the rotational frame, moments of inertia. We'll see all of that from chapter 8. Chapter 9 was on fluids. Listen, chapter 9 is really a hodgepodge of different things, and you need to be able to sort of learn to distinguish between those different things. So we'll see pressure at a certain depth, pressure measurements like manometers and barometers. You'll need to know how to approach all those problems. Now, we've done similar problems in class, and look at the homework, and I pulled problems from the OpenStax quizzes as well. Not from the personalized questions, those are different for everybody, but from the questions that I assigned you. So I'll look back at all those things for chapters 8 and 9. And you didn't have an OpenStax quiz for chapter 10, but look at the homework and look at the old questions from the test. For chapter 10, that was the ideal gas law, linear expansion, and I'm missing something. What was it? Temperature scales. Fahrenheit, Celsius, Kelvin, how those scales are set up, what they measure, what they're based on, and then also how to convert between the different scales. Make sure you know your equation sheet. I'll give it to you on Monday, but just make sure that you're familiar with what's on it. That's the big thing on chapters 9 and 10, is that there's a lot of information on that equation sheet that won't be in the problem. I know that on previous problems, one of those questions I often give, the densities that you need, or the coefficients, or the ideal gas constant, all those various things, but that's not the case for this exam. I've been telling you this, so hopefully you've been sort of looking at that equation sheet over the past week or two, and you just know that it has densities, it has specific heats, it has coefficients of linear expansion, it has the ideal gas constant, that R value. There's a lot of information, so just make sure that you're familiar with it. Okay? Right. Before you go to bed at night, just put it between your face and the pillow. And then when you roll over in the middle of the night, you'll look at it as you roll through your pillow. Okay? Whatever you got to do. Take it to your refrigerator or whatever. Okay? All right, I'm going to step through the different types of things. Are there particular problems that we want to look at? No? All right, so let's go just sort of chapter by chapter. Chapter 8, you will see torques. So I know that we had a problem like this where you had different forces acting on the bar. You're going to see that again because it comes up as we do Newton's second law. So you will see a problem, something like this, where there are some forces and there's some angles, and I ask you, what is the net torque? All right, I will also ask you to calculate, given the net torque, what is the angular acceleration? Now remember Newton's second law, F equals ma, can also be written torque equals I alpha. So if we know the net torque, then we can find the angular acceleration as long as we can find the moment of inertia. Now remember, with moment of inertia, there are two ways, two different approaches that will deal with the moment of inertia. One is a particle. So if I have a mass on a string like that, or we've dealt with particles in different ways, like I had a kid jump onto the edge of a merry-go-round, we treated that like a particle. Or in your homework, you had like a lump of clay on a potter's wheel, that was a particle. And in those cases, we calculate the moment of inertia as I equals mr squared, where this is r, this is m. R is just the distance to the axis of rotation. And then also a rigid body. And a rigid body is where we have a cylinder, or we have a rod, or we have a sphere, or any number of different bodies that we have on that table on your equation sheet. So you need to be able to understand when you deal with which. Right? And you can look back at the old homework problems and the old questions that we worked in class and on the old tests to help you practice that. But you will have several problems where you have to figure out the moment of inertia. And then also, like we did in class, you need to be able to, given an object, figure out what are the relative moments of inertia. The problem that we had in class was one like this. We did a couple variations of this. Remember where I had the T-bar, and I asked you what is the moment of inertia around different axes, and you had to rank them? You'll have some similar questions to that. I think just one question, where you have to rank the moments of inertia. And remember, in those, you want to ask yourself, in which of these has the most mass at larger radii? A mass at a large radius will bump up the moment of inertia because I go by that mr squared. When I ask myself, which has the most mass at the largest radii? You need to know kinetic energy. You know, mostly this is just sort of plugging in the right equation, that our kinetic energy is 1/2 I omega squared. That's our rotational kinetic energy. Also remember that I can calculate the work is equal to the torque times the angle theta. Remember before in chapter 5 or 6, we had work was force times displacement. So this is like our rotational equivalent of that. I think your equation sheet in the back of your book doesn't have that, but the new equation sheet that you'll get is online, and you'll get it in your exam on Monday, does have that equation. That's not all, is it? Oh no, so also angular momentum. So you'll have some problems. We worked through several different kinds that deal with angular momentum. Remember, angular momentum, L, is equal to I omega. These are a lot like those problems, the P equals mv problems that we worked back in chapter 5, I think, or 6. L is equal to I times omega. This is the moment of inertia right here. This is our angular velocity or angular speed. We have a couple different problems of these, and we have some in the homework. And those are problems where the object that you're dealing with changes its moment of inertia. So like in the homework, I think you had one where you had the 4 particles, and they moved to different radii, and that changed the moment of inertia. That's a lot like the figure skater. She pulls her arms in, and that causes her moment of inertia. Let's see, to go up or down. Down, right, very good. So because I moved mass in, and that causes my moment of inertia to decrease, which causes your speed to decrease. And so you could have some calculations that are similar to that, similar to the homework, where you have this single body that actually changes its moments of inertia. And in that case, you would say I initial, omega initial equals I final, omega final, and then recognize that if this goes down, then this must go up, but also be able to calculate what that omega final would be. You could also have problems, and we've seen some like this, where I have two objects that are spinning. So say I have an object, say a disk that's spinning like that, and a rod that's spinning like that. They both have an angular momentum, I1 omega 1 plus I2 omega 2, whatever those are. They both have their angular momentum separately, but then let's say that they come together. Like I have a big flywheel that engages with a spinning bar in some way through a set of gears. Then they would have the same speed, and they would be traveling at the same omega. Then that would be I1 plus I2 equals to omega final. This is a lot like our perfectly elastic collisions, perfectly inelastic collisions, where the two masses stuck together and then moved off at the same speed. It's the same idea here. Our two objects stick together and then they rotate at the same speed. So just like in those perfectly inelastic collisions, I would add up the masses. Here I add up the moments of inertia. So I think that's it for chapter 8. Let's just take a look. I'm going to take a look at some of the old tests for chapter 8. And then you guys just sort of holler out. We've worked some of these in class, but you guys holler out if you see some that you might want to look at. Now, this is fall 15, actually. This one is in the back of your book if you want to look at this one. Here's a solid sphere with in its rotational kinetic energy, moment of inertia, right, number 4. Okay, good. You will have a problem like this. It's not a T-bar, it's a different shape, but the same process would happen. Here I wanted to know, I want you to rank the moments of inertia for this object. This is 2 bars that have 2 equal lengths and mass, and then you stick them together like this, and I want to know which rank them from largest to smallest moment of inertia. Listen, on these you want to start just by eliminating some things. So you want to first ask yourself, around which axis does it have the biggest moment of inertia? The axis where it has the biggest moment of inertia is where you have the most mass at the largest radii. So notice axis A. If about axis A, this thing rotates like this, I have all this mass at the biggest radius possible, and then I also have additional mass that goes out to that radius. So about axis A is going to get my biggest moment of inertia, and so I know it's either A, B, or C. I can get rid of D because it shows ID is the biggest. And then I want to ask myself, which is the smallest moment of inertia? Well, let's see, it could be this one, where I have only this bar rotating, or it could be this one, where I only have this bar that's rotating about the axis. Which do you think it is? This one or this one? Which is the smallest? The first one or the second one? The second one has the smallest moment of inertia because I only have this bar, which is contributing to the moment of inertia. This one's not at all because r is equal to 0, rotating about axis D. And so rotating about axis D, I only have the mass goes out to half the radius, half the length of the bar. So the moment of inertia about axis D is the smallest. So that gets rid of A. So far I've gotten rid of D and A. And now I want to ask myself the question, how does C compete? Because option C says that IC is equal to ID. But that's not the case. These are different scenarios. So I have to get rid of C, and then that just leaves us with option B. So we had some concept test questions in the clicker questions. I'll look at those and sort of think about in similar situations and think about how that mass is distributed. If I have mass along the axis of rotation, it doesn't contribute to the moment of inertia at all. And that's really what's important there. And then you're looking at what mass, which object has the most mass at large radii. Those are kind of tricky. but you sort of have to think about how the mass is distributed. You will have questions. Okay, just one question. Rachel, is that okay for now? All right. Here's a moment of inertia. You have to add up the two moments of inertia. As I said, you will have a problem like this. I understand that we had one similar to this on the previous test where you have to find the net torque. But in addition to that, you'll have to find the angular acceleration and maybe something else, or no, just the angular acceleration. All right. Anything stand out on this? I'm going to go on to chapter, I'm sorry, number 10. Okay, gosh, these are tough, right? Ranking the torques. You aren't going to have a question on number 10 though, because we did this in the previous test. Okay, so you won't have to rank torques like that. Is that okay if I skip it? Okay. But it could have it for the final. All right, well, let's go on then to chapter 9. Well, chapter 9 had, as I said, a hodgepodge of things. It's going to be important to think about your equation sheet and what it has on there, because you'll be able to use it a lot for chapter 9, but you need to know how to use it. Just having the equations in front of you doesn't mean that you're going to work the problems correctly. You need to be able to know what the problem is talking about, be able to know what is the information that you have that you don't have, that you also have on your equation sheet in those various tables. Okay, so let's see. We know the phases of matter. I think y'all know that. Also, just sort of a little bit about dark matter. Dark matter is dark. It doesn't emit or reflect light, and it makes up most of our universe, about 95% of our universe. That's really all you need to know about dark matter. Phases of matter, you know, solids, liquids, gases, plasmas, ionized gases. Could see a stress and strain problem. That's using the Young's modulus F over A. And by the way, this is our definition of pressure, is equal to Y delta L over L. The tricky part on these is just knowing what these various quantities are. This is our force. This is our unit area. Be careful on these, because sometimes I'll give the area and sometimes I'll give the radius or the diameter. Just be careful when you're reading the problems. I try not to give too many extra steps, but you know, sometimes I like to give you extra steps. So just read the problem very carefully, but you know, not too carefully, not too slowly, but read it carefully enough that you get the appropriate information. I like to go through when I'm reading the comment and just circle the words that are really important as they stand out to me. Oh, it's the diameter. Let me circle that because I'll need to have that and make it into a radius or make it into an area. The Young's modulus, you're not going to have it in the problem, but it's on your table. This describes how much things stretch when you pull on them, when you apply a pressure to them. Delta L is the amount that it stretches, and then L naught is the original length. We can look at some problems like that on some of the old tests. Also, density and pressure. Density. Rho is equal to M over V. You can just have a basic question. I give you a mass and a volume and ask you what the density is. Likewise, as I said, pressure is F over A. You could have a basic question, like in, I don't know, you have some questions in the open stats and the old test and the homework. I give you a force, I tell you a surface over which it's being applied, and you might have to find the area, but then you have to find the pressure. Just be careful that you read it carefully and determine if I'm giving you the area or if I'm giving you the radius or the diameter or the dimensions of that material. We also had pressure at a certain depth. Remember, that was where I wanted to know if I'm a distance h, what is the pressure? That pressure is equal to P naught plus rho GH, where this pressure is P naught. So whatever my pressure is here is equal to the weight of the column that sits on top of it, that's given by that rho GH, plus this extra pressure that's pushing down on top of the surface of the liquid. That comes up too in our manometers and our barometers, and using that because it operates by the same principle, that I'm considering the pressure of this column of liquid that sits on top of a point. Pascal's principle. Remember Pascal's principle, and you need to know in general the basic principle, the basic idea behind each of these principles. Pascal's principle says that a pressure is felt throughout. A liquid. That is an incompressible fluid, which really just means liquids. We'll do Pascal's. Let me just sort of summarize the others that were important. The equation of continuity, that was at A1 V1 equals A2 V2. This is based on the conservation of matter, that in a system that has no incoming or outgoing material, then matter is conserved. You can't just destroy matter. That's the equation of continuity. And then Bernoulli's principle. This was based on the conservation of energy. Conservation of energy. So just sort of know those basic ideas behind those different principles that we discussed in Chapter 9. Now, Pascal's principle, you're going to have a hydraulics problem. The basic one that we worked in class, and they're all basically the same, is like this. I put a pressure or a force in here, F1, call this A1, F2, I get out, A2 here. Pascal's principle says that the pressure is the same throughout a liquid. That means that P1 equals P2. You will have a hydraulics problem like this. It might look like this, or we've had different variations. I think you even had one on your OpenStax quiz. But I take my input pressure, F1 over A1, and then that's equal to my output pressure, F2 over A2. You will have a hydraulics problem. All right, you're also going to have a manometer or barometer. With those, sort of a two-step deal. I have a pressure over here that I want to know. I have a known pressure over here, P naught, and then I have liquid. And I know the distance, h, between these. Remember, with these, first you have this, you know that P is equal to P naught plus or minus rho GH. You need to figure out, do I use plus or minus? And then you just want to ask yourself, is this P, is it bigger or smaller than P naught? Well, in this case, P is smaller because P naught is able to push this liquid down and push it up here. That means that P is not big enough to balance out P naught. So if P is smaller, that means I'm going to use the minus because P is less than P naught. So you need to figure out, was this plus or minus? Which do I use for that? Otherwise, they work largely the same. Remember, this is your density of the fluid. This may or may, it's probably not going to be given in the problem, but it's in the equation sheet. I have a table of densities there. The big ones are water, which, you know, it's good just to know the density of water. What is it? If I have a kilogram, or excuse me, a cubic meter of water, that's how many kilograms? 1,000, right? Water's pretty heavy, actually. Water has 1,000 kilograms per cubic meter, or 1 gram per cubic centimeter. But if you ever doubt, always go to SI units. And our SI units for density are kilograms and cubic meters. If ever in doubt, go to SI units. But as you know, it's not always necessary. Look at your units closely, especially on this exam. It'll help you to look at your units closely and think about, do I need to convert the units? What do I do? But if you're ever in doubt, just convert them to SI units. And then if you need to convert them back to the other units, which are listed, then do so. But just a little hint, usually if the units in the problem are the same as the units in the answers, then you don't have to convert units. Is that usually true, or is that always true? For me, it's always true, but like MCAT, stuff like that, it's often true, not necessarily true. Okay, but I'm nicer than the MCAT people, right? You don't even know any MCAT people. How do you know? All right. MCAT's pretty tough. I really treasure you people that take it. Okay, Archimedes' principle is to find our buoyant force. Keep your subscript straight on this. Our buoyant force is the density of the fluid times the volume of the object times the acceleration due to gravity. Also, look back at our concept test because we had some good questions about buoyant force and how it affects different things like, you know, like you throw the steel into the lake, what happens to the level of the lake, or the ice does this or that. All right, look at those types of questions in the concept test. In general, that's true for all the material, but we had some good questions on buoyant force. I think also in the OpenStax quiz we had some stuff. And then equation of continuity. Equation of continuity was dealing with pipes like this that go from one area, A1, one speed, V1, to a smaller area, for example, A2 and V2. And it's driven by this equation, A1 V1 equals A2 V2. Remember, this is the conservation of matter. It says that whatever flow of fluid I have here, I also have to have here. If my area goes down, that means my speed goes up. And you can calculate that, and you might have to calculate that, or you might just have to, I ask you, is the speed bigger or smaller here? Those sort of questions, which we've seen before. That's the equation of continuity. And then we also had Bernoulli's equation. Bernoulli's equation, let me think. I'm pretty sure that you didn't have to calculate anything for Bernoulli's equation. I don't remember. I know that you don't have a scenario where you have the pipe changing height, which makes it a little more complicated. P1 plus 1/2 rho V1 squared plus rho GH. Bernoulli's equation says that this is a constant, that the sum of all these energies at one point will be equal at the same point. But you don't have any scenarios where I change height. So for all sakes that we're concerned about, we'll just forget about this term because H will be constant. So the result of Bernoulli's principle is that if the speed goes up, the pressure goes down. And we had several questions about that through the class and in the various assignments that probe that. That when our speed goes up, our pressure goes down. And that's an important principle that's in a lot of different health applications. That's Bernoulli, just based on the conservation of energy. Okay, that's all for that chapter. Let's look. So we'll just sort of keep looking here. Number 11 here is Archimedes. 12, likewise, is Archimedes' principle. 13 is Bernoulli's. Number 15 is Bernoulli's, but you actually have to calculate it. I don't remember if we have anything like that on the exam. It could be, where you have to calculate the pressure based on Bernoulli's principle. Here's a hydraulics problem. As I said, you will have a hydraulic problem. It may or may not look like this, but it'll be approached the same way, where I set the pressure at one spot equal to the pressure at the other spot. Manometer, you're going to have a manometer or a barometer. Remember, manometer and barometer are the same. The only difference is that P0 for a barometer is 0. It has a vacuum. Okay, I think that's about it. Oh, here is linear, or not linear expansion, stress and strain, elasticity of solids. So when you apply a pressure to something, it stretches. Anything stand out to y'all that you want to have a little extra fun on? Yeah. They work out a lot the same, except for a barometer. P0 is equal to 0. P0 is that known pressure. A barometer looks like this. Like this is a manometer. A barometer looks something like this, where my fluid comes up, and right here, P0 is a vacuum. It's equal to 0. So barometers are a little easier to deal with because you don't have to worry about, oh, is it plus or minus? It's going to be a manometer. It's not going to be a manometer. Okay. All right, let's look at the last chapter. I want to say it's easy, but you know, you've seen it for the most of you have seen the next chapter. Chapter 10, temperature scales. Know what they're based on, know how to convert them. You need to know Kelvin, Celsius, and Fahrenheit. Useful just to know some basic temperatures in the Celsius scale, room temperature, you know, body temperature, that sort of thing, freezing point of water. Need to know linear expansion. Particularly like we had in the concept test, and I will post those concept tests today. Sorry, I meant to do it earlier. The ones that we did on Wednesday, some of you came on Wednesday and we went through those concept tests, and the screencast is on, so if you want to go and look at those, that's fine. Or I'm going to post the answers today on the concept test link on the website. But for the linear expansion, make sure that you understand what to do if I have two parts of differing materials, how they respond to changes in temperature. So for example, in the concept test, we had a ring that was made of steel or aluminum, I forget, and there was a rod that was made of some other material, and it asked, if you heat this up, will the rod eventually touch the ring? And you had to think about how these different materials expand as they change their temperature. Look back at that. We'll look at some of the old tests and think about that as well. But you'll see a question likely that's similar to one of those. And after linear expansion, this ideal gas law. Wrapped up in that also is the concept of a mole and the ideal gas law, PV equals nRT. Big thing with this is to watch your units. All right, temperature needs to be in Kelvin, volume in cubic meters, and the mass in kilograms. Everything in SI units. Kelvin is the SI unit, so make sure you check that. Sometimes I ask for temperatures that are not in Kelvin, but in Celsius, because that's the more common scale that we use. But if you're using the ideal gas law, it has to be in Kelvin. If you ever forget this, just look at the units on your constants. The ideal gas, gas constant, the universal gas constant R, if you look at the units, it has a K in there. So just, if you ever forget, just look at those units. That will really help you. I know those of you that are doing really well in the class, I know that you spend a lot of time thinking about the units, or you sort of got into that habit. So it is a useful practice for you to think about the units. Alrighty? I think that's it for that chapter. Yep, that's it. Let's look at the test. Some calculations that you'll have to do. Just sort of ideas about how things change based on the ideal gas law. Here's the linear expansion. Conversion. You have those equations to convert, so you could probably figure it out from that. All right. Olivia? This one? What, 20? We didn't do, this was in the lab, we didn't do this. Yeah, sorry, that's in chapter 11. We didn't get into it. We could probably eke out chapter 11 today, though. Y'all want to do it? No, I don't. No calorimetry. Y'all did that in lab, though, right? Anything else, y'all?
On the flash freeze.
24. Yeah, so this is our linear expansion. How does it go? Delta L Gosh, what is it? Forget. Delta L is alpha L naught delta T. All right, and so once we realize that this is dealing with linear expansion, then I need to figure out what is delta L. So I'm looking for delta L here. I know alpha for steel. I go to my equation sheet. And I find alpha for steel is 20, oh, that's Young's modulus. For steel is 11 times 10 to the minus 6. And also I notice that that's degrees Celsius to the minus 1. L naught is 25 meters. And delta T, it goes from 0 to 40. So my delta T is 40 minus 0, or that's 40. So I get 40 times 25, that's 1,000, times 11 times 10 to the minus 6, that's 11 times 10 to the minus 3. Oh, but that's not on there, right? But I'm asking for the length of the beam on this hot day. It was 25 meters, so now it's going to be 25.011. That's 11 times 10 to the minus 3 added to 25. Is that okay, Nick? Yeah. How y'all feel about this exam? Yeah, chapter 8 is the hard part on this exam. So if you're running short on time, I would focus on chapter 8, but you really need to focus on all three. With chapter 10, you probably know chapter 10 because you've had it before. But chapter 8 is probably the hardest part on this exam. All right. Well, I think let's go out there, but I don't really have anything else. Oh, we will meet in the auditorium, okay? If you have more questions, feel free to hang around, okay? We're going to go to my office.